Hi, today we're going to do 8A for statistics. I'm Carly McAvoy, and I think this has about 25 questions, so it's a little longer, but the questions won't take you that long if you understand what's happening. Number 1 says the mean weight of beauty pageant winners is 121 pounds. A study of 15 randomly selected beauty pageants resulted in a mean winner weight of 120 pounds. So the claim originally is that the mean weight is 121 pounds. That's what they're saying. This little sample was slightly different, but when you take a sample of people, especially just a small sample like 15, your mean for your sample may be a little different than the actual claim. Express the original claim in symbolic form. Because they talked about a mean weight, then we're talking about mu. We have choice of mu, standard deviation, or the proportion. This one they're talking about mu. And they're saying that the weight is 121. They didn't say less than or greater than. And so we know that it's equal to 121. That's the claim, that their mean weight is equal to 121. Okay, identify the null and the alternative hypothesis. Remember, the null hypothesis is the one where we can have equal to parts. In theory, we could have any of those symbols for our null hypothesis. We're going to just be working with the equal sign. But anyways, we have all those choices. And so when the null hypothesis is this, it's saying that the mu equals 121. Since they said equals 121 in their claim, that is our null hypothesis. It's the same. The alternative hypothesis cannot have, sometimes you see null A. This one in this book they do null 1, but alternative or 1 or 0, whatever. This one is saying the mu. We're always talking about mu because in the whole problem now we're going to be talking about the mean. And this one's saying that this study says that the mean weight was 120 pounds, but we don't. Later on, we might look at that. But right now, when we're talking about the null and the alternative hypothesis, we're just looking at the original claim. We're not talking about some sample they did. The original claim was that the mean was 121. So since they said equal to, we're going to say, well, the alternative is that it's not equal to. So we would just do that. And that means that it could be greater than or it could be less than. And so that's where they get the why they get the not equal to, if you look at it, because that if they had said that the average weight is less than 120 pounds, then that's different. But because they said it equals 121, then we do the opposite, or the null hypothesis is equal, the alternative hypothesis is not equal to. Okay. At least 35% of internet users pay bills online. At least 35% of internet users pay bills online. Okay. A recent survey of 341 internet users indicated that 37% pay their bills online. Again, this piece isn't what we're talking about. We're talking about the claim. Okay, this is a separate piece that we might use later when we did an entire hypothesis problem, but right now we're not. Express the original claim in symbolic form. Well, first of all, we're talking about a percentage, so that's a proportion. So I know that I'm talking about p here, not mu or standard deviation. And then we'd say, well, it's at least. So if you're talking about going out to a bar and you say, well, in order to get in, I have to be at least 21. Does that mean you could be less than 21? No, it means you have to be equal to 21 or greater than. So the claim that they're talking about is this. I don't know if they, put it in 0.35 form. The claim is that it's greater than 0.35, greater than or equal to. If it's at least, it's greater than or equal to. Identify the null and the alternative hypothesis. Well, the null and the alternative hypothesis have to do with the claim, which has to do with 0.35. So you could just ignore the 37. That's just thrown in there to see if you'll go for it. Don't. Okay, so the null hypothesis can have the zeros in it. I mean, it can have the equal to's in it, sorry. But we don't really use this form when we're doing this. That's this claim, but we're going to change it when we make it into the null hypothesis, and we're just going to use the equal to part. So the P is equal to 0.35. That's the claim. Okay, we say that's the claim. And then we want to say what the alternative hypothesis is. Where's my... we want to do the opposite of what they say. So if they're saying that it's greater than or equal to, then we say, well, maybe it's exactly equal to. And then in order to sort of dispute that or look at the opposite of that, we say P is less than 0.35. Because it's like saying, you're telling me that 35% of internet users, more than 35% of internet users pay their bills online. I want to test it and see if I can get a sample where it's less than that. Because if it's less than that, then I can say that you're not being honest, right? So we always look at like the opposite of the claim. Since the claim was greater than or equal to, we're going to look at less than. We don't put an equal to part here because we never use equal to in the alternative hypotheses. And that was 827. The first one was, if I didn't say it, 825. So those are from the beginning. All right. You know the answer. That's okay. Make a decision about the given claim. Do not use any formal procedures and exact calculations, just the rare event rule. A rare event rule means if it's really small percentage, which we usually use 5%, then we say that that's probably not going to happen by chance, you know. So a coin favors heads when tossed. That's the claim. And there are 12 heads and 26 tosses. So we're talking about a probability of proportion here. And if I did the 12 divided by 26, I get 0.4615, I don't know, about 46% of the time. Well, 26 tosses is not that many. It's possible in 26 tosses that you're not going to get exactly 50-50, which is what you would expect from a coin. So I don't think there's any evidence, because this is a pretty reasonable thing to happen, right? If it was 0.05 or less, then we'd start to say, wait a minute, that's kind of rare. But 46%, that's not rare. And so we would say, there is not sufficient, because there are substantially more, there are not sufficient evidence to support the claim because there are not substantially more heads than tails. I mean, there's 14 tails, 12 heads. That's pretty close. That would be very common of what you might have if you flip that. So we don't think that's rare at all. Okay. All right, make a decision about the given claim. Use only a rare event rule. Make subjective estimates to determine whether events are likely. For example, if the claim is that the coin favors heads and his sample results in 11 out of 20, conclude there is not sufficient evidence to support the claim because 11 out of 20 is pretty typical when it's a 50-50 chance. Okay, the claim is the mean pulse rate of students in a large statistics class is greater than 71. A simple random sample of the students has a mean pulse rate of 71.3. Well, 71.3 is pretty close to 71, right? I mean, in fact, if you're talking about a pulse rate, if you were counting it just by hand, you probably wouldn't even notice the difference of 0.3 seconds, right? So the claim being 71, our sample being 71.3 means that it doesn't seem, there's no evidence to suggest that the claim is wrong. We didn't get any evidence that would say that. Now, if we did this and got 79 or something, we'd say, wait a second, that doesn't seem even close to what ours was, but ours is close. So the sample is not unusual if the sample is not unusual if the claim is true. The sample is not unusual if the claim is false. Therefore, there is not sufficient evidence to support the claim. The sample is not unusual if the claim is false. Well, first of all, I want to say the sample is not unusual if the claim is true. So we're on C and D. I'm just eliminating A and B because they both say the sample is unusual. It's not. The sample is not unusual if the claim is false. Well, we don't know about the claim. I mean, it's near that, but it doesn't give us anything to say. We don't have enough evidence to go on. So I think we have to say there's not sufficient evidence to support the claim. Yeah, because it seems like it's pretty close, but it could be something different and we could be fine. I mean, the claim could be 72, you know, and 71.3 would still be fine. Or, you know, like there's so many other claims that could make that true that there really isn't enough evidence. All right. The claim is that the proportion of peas with yellow pods is equal to 25%. The sample statistics from one experiment includes 490 peas with 128 of them having yellow pods. Find the value of the test statistic. All right, so a test statistic now is different than a critical value. It's a little different, okay? But it does kind of give us that point to look at to say, like, is that common or is that not common? Remember that we say that if a z value is within 2, -2, +2, then we say those are usual values. So we're looking at test statistics that come out like far to the ends, you know, something greater than 2. Something like a 7, well, that's definitely strange, you know. But anything within the boundaries isn't too strange. So we need the little formula to find the test statistic. I don't have that memorized. Maybe after seeing the notes you do, but I'm gonna go find it by letting my friendly, useful little math program help me out. Do an example. We're looking at we know what P is, so we know what Q is. Okay, there it is. All right. Right, so let me write this down. The test statistic, or the z-score that I'm interested in, comes from p hat minus p. You know what p hat is? It's the number we're going to find by taking 128 and dividing by 490. The p is given in the problem to be 0.25. Oh, I just said it, but you're not seeing it. And then, and then over the square root of, I just finished just teaching statistics in the spring, and I've already forget these formulas. This is the whole thing now. You know that this stuff exists, and now if you're out in the world and you ever get asked to do something like this, well, you can just go look it up. You don't have to memorize. That's not where I want to be. Where do I want to be? Here. You don't have to memorize formulas. You use them when you need them. You know, you can go get them offline when you need it. Okay, so let's find out what our p hat is. 128 divided by 490. It should be around 25%. It's 26. I would say 0.26. I could say 1. I'll maybe do that. 0.261. There we go. Is our p hat. We know what Q is because we know the answer. I'm not going to worry about that. Q is 0.75. How did I get that? 1 minus P is that. So I have everything I need because I also know what N is, which was 490. Right? That's all that I need for that. So my Z, or my test statistic, it's that one point that I'm looking at to see, does this make sense, is P hat 0.261. Notice that if P hat was less than my P, I'm going to get a negative value, and that's fine for Z's because you can be to the left of 0, then that's a negative value, and to the right is a positive value, so it's good for us to be able to see whether it was negative or positive. So don't just always put the greater number in the front, put them in the order that you see them. P is 0.25, Q is 0.75, and over the whole thing we have 490. People have trouble entering this in their calculator, so you want to practice that. You don't want it to be your calculator skills that is your downfall when you're doing the final, right? When you come in to do the final, so be careful. Here's what I would do for this. I would do the 0.261 minus 0.25 and just get that answer, which is 0.011. I'm not changing anything, and I'm just going to say divided by. Then the top is divided by, and what it's being divided by is a square root that's got a fraction under it. And then I do 0.25 times 0.75, and that is 490 for my n. So I've got everything entered. I just went ahead and did the top part. You don't have to do that. You could have just left that in parentheses and not hit enter, but I usually do. And that gives me 0.5623. They asked us to round to the hundredths. And if you look at my answer, it rounds to 0.56. So what did I do? Well, I put this to 0.261. Let's do 0.26 and see if we get a closer answer. See how I did that? I left out 3 places. 1 decimal will make a difference. So let's see if it makes a difference. So let's do 0.26. Well, I'll show you this way. 0.26 minus 0.25 in parentheses, and then I hit divide. You got to put parentheses around it if you're not going to hit enter in between. And then I'm going to divide by the square root of the fraction, and I have 0.25 times 0.75 over 490. So I kind of didn't simplify it there. I left it all there. Whoa. And I got 0.51. So that 1/10 is throwing it off. That's pretty weird, huh? But anyway, we get in the ballpark, and they're going to have a little tolerance there for that. So pretty interesting how different your answer can be just by leaving off. I mean, 1,000th. It was 1,000th different. So let's see if let's just make sure I didn't do something crazy and kooky in there. Divided by, whoops, no. I wanted to do the 0.26 minus 0.25. Divided by, it's okay to practice and see what happens. 0.25 times 0.75 over 490. Yep, 0.51, so that changed it quite a bit. So I'd go out 3 places. Probably if you went out 4, you might get exactly what they had, but they will have some tolerance built in, so that should work out. Okay, the claim is that the proportion of adults who smoke a cigarette in the past week is less than 0.30. And the sample statistic is include n equals 1169 subjects with 374 saying they smoked a cigarette in the past week. Find the value of the test statistic. So we know what P is because we're given 0.3. If we're talking about writing the null hypothesis and the alternative hypothesis, we'd actually have to include think about that less than thing, but we're not doing that. We're just writing down the claim as it's given. We're always going to use an equal to for that. All right, so then the p hat is 374 divided by 1169. Okay. And that's 0.31. I'll go out 2 places, 99. If I do 0.32, it would be different, right? What's Q? Well, 1 minus 0.3 is 0.7. What's my N? My N is 1169. And that's all I need to find that test statistic. So this is a Z-score that kind of shows me where I'm at. If it was 0.57 like we had here, remember if it was at the mean, that would be a Z-score of 0. So a Z-score of 0.57 is just to the right of that, right? So I'm saying it's a little more than, and it makes sense because 0.25 was our mean, and a little more than that was 0.261. So it makes sense it's to the right because it was greater than. Anyway, what we have here is 0.3199 minus 0.3 divided by the square root of 0.3 times 0.7 over 1169. And let's see, 0.3199 minus 0.3. And then I do divided by second function square root, the fraction symbol, 0.3 times 0.7 over 1169. When you do your things in bits and pieces, Here I got 1.48. Pretty close to what they had, but they had 1.49. Again, different calculators are going to round things a little differently. But if you do your calculator in bits and pieces and write that down and then delete that and then go write that down, and every time you're rounding, you're going to get an answer that's too far off. Try to enter it all at once. Okay? All right. We're on to number 7. Dun, dun, dun. Is it the same? Because if it is, I'm not going to do it. A claim is that the white blood cell count of adult females are normally distributed with a standard deviation equal to 1.84. Ooh. Standard deviation, right? The random sample of 39 adult females has white blood cell counts with a mean of 8.45 and a standard deviation of 3.93. Find the value of the test statistic. Well, do we think it's going to be a different way to find it if it's the standard deviation, or do you think it's going to be the same? And if you're not sure, then come over here to your handy dandy Math Excel program and do view an example. The correct test statistic must be chosen, right? The null hypothesis is about the standard deviation, so it's chi-squared is the correct course statistic to use. That should make sense. When we did homework 7B, we were using that for that. So the requirement to use that is satisfied. To find the test statistic, the formula for the test statistic is down here. For chi-squared, we have n minus 1 s squared over, the standard deviation is given that way. The s squared is the sample variance, and this is the claimed population variance. So we have both things. They're claiming this is 1.84. Our sample variance is actually, you can't see what I have there. Anyways, let's go back. Okay, so we know what S is because it was given. We know what the sigma is. Sigma is our population standard deviation because that's given. And we know what N is because we know that N is 39. Right? So we can do this. We can find that test statistic. We're interested in using the correct one, either Z or T or chi-squared. With standard deviation statements, we want to use the chi-squared. Okay, so I'm going to do this is n minus 1. I'll just do that one. Okay, in my head. That's 38. And then I have 3.93 squared, and I have 1.84 squared. All right, so I'm going to do that on my calculator. I'm going to just put my fraction button in. 38 times 3.93 squared over 1.84 squared. And what I get is 173.35. Our test statistic is that. So that's huge. Look how far away. We're supposed to be at 1.84. Our sample is 3.93. It's extremely different. So it's an extreme test statistic. Quite large, right? Makes no sense. Okay, I mean, it shows you, it makes sense. It just tells us that, yeah, we did not find what we were supposed to find or what we thought we were going to find there. We found something quite different. Okay. So they do we got all kinds of pages of stuff here because they have the print off at the negative and the positive z-scores. You are going to not need that. You're going to be using the calculator. Okay, assume that the significance level is 0.05. Use the given information to find the p-value and the critical value. A significance level of 0.05 means that if your p-value is different. I mean, you look at it and you compare your p-value to that 0.05 or 5% level. If, remember this, I'm sure I talked about it in the notes. If the p is high, the null will fly. What does that mean if it's high? It means if p is greater than 0.05, because that's the level of significance that we're using. That's randomly given to us. They might say, oh, the significant level is 0.01 or 0.02. 0.05 is the most common, so we see that a lot. What does it mean if the null will fly? It means that the p-value is the p-value, if it's high, I'm sorry, I started reading something in the middle of talking. If it's greater than that, it's high, and that will fly means that we accept the null hypothesis as given. It will fly. We will accept it. We never say accept really in statistics, but that's kind of what we mean. Whereas if the p is low, then the null must go. So that means that we don't believe the null hypothesis if our p-value is low. In this case, it was less than 0.05. But you can see here, the testing the claim that p is less than 0.07. The test statistic z is 1.80 is obtained when testing the claim that p is less than 0.7. What is the p-value? Okay, so p-value has to do with this area under our curve. We have it specifically talking about something, so we call it a p-value, but we've already talked about the probability under the curve. And so we have a z-score of 1.80. If our z-score was 0, we'd be right there in the middle. So negative 1.8, if this was 1 and this was 2, here, right here maybe is our negative 1.80 z-score. So obviously it's to the left of the 0 because it's negative, that makes sense. We want to know what the p-value is, and so we're interested in finding the area to the left of this, okay? Because it says less than, we're talking about a less than statement, so we're interested in the less than of that. How do you find the area under there? Well, that's that's normal CDF. I almost said it, but I didn't. Okay, so we're doing second function data, distribution, normal CDF. Our mean is 0, our sigma is 1, our lower bound is negative infinity, goes forever. Our upper bound ends at negative 1.80. That we've done before and that you know how to do. And so what we get is 0.0359. We're going to 4 places, yeah. So we get 0.0359. That's just the area to the left there, right? So our p-value is 0.0359, which is less than 0.05. If the p-value is high, the null will fly. But we just found that our p-value is low. It's lower than that. So that means if p is low, the null must go. So we don't believe the null hypothesis because we got a really small p-value. But one of the things they want to know here is what's the critical value of the critical value of that. Now we did critical values a couple of homework assignments ago, maybe 2 homework assignments ago, and the critical value is the point that would be acceptable, where the cutoff is, like what would be the 0.05 point. We're using 0.05 as the interesting thing there. So we want to know, we're basically asking what would the value be that would kind of be the separation between the usual and the unusual values. And so if you think about it this way, we want to know, obviously ours is too far out, you know, because we have a p-value that's unusual. So we want to know what's the cutoff point, sort of like this. This is the unusual values over here, and these are the usual values over here, right? And the question is, when we're asking a critical value, what's that point? What's the z-score right there that makes it of usual value? Well, we're talking about 0.05, so in my calculator I'm going to put an inverse normal, and then for my area I'm going to put 0.05, and of course mu is 0 and sigma is 1, and I'm going to find that critical value that way. Now it's definitely to the left because we're talking about less than of the 0 point, so I would expect a 0 critical value. So I'm going to go to this again. I'm going to go to distribution and go down to inverse normal and put in the 0.05, which was my critical, which was my significance level, and then my 0 and 1, and hit calculate, and that gives me negative 1.6448, and the book keeps calling it negative 1.65, but I'm going to go with 1.645. And if it's to two places, then see what I actually get is negative 1.6448. So if I round this to the second place, it should round to 1.64. The book has 1.65. I don't know why, but it is negative because it's on that left side. So this is the value that separates the unusual from the usual. So it's not crazy then that ours was unusual because ours were further left, which put ours into the unusual values, right? And if we got something that was greater than negative 1.645, something over here, it would have been usual, and we would have said that null was high. But, I mean, the p was high, but in this case, we said p was low, so it must go. So the critical value is that one over there on the left. Again, they have 1.645, and I think it's 1.64. But that's what we're doing there. We're looking, first of all, for the p-value, which is just the area to the left of our particular z-score. And then we're asking for the critical values. Well, that critical value is the point that separates the unusual from the usual. Okay. All right. So done with that. And that. I just got so much to look at here. It's hard to keep it all straight. Okay. So use a significance level of 0.05. And do I have a couple more pages of stuff here? Yes. All right. Assume a significance level of 0.05 and use the given statement and find the p-value and critical values. Well, my p-value is the area under the curve that's different from my test statistic. Okay, so we want to find the area. Here's z over here. My z is negative 1.62. And so I'm interested in what's the area to the left of that. Okay, well, which do you use? Inverse normal or normal CDF? I don't want to say it because I want you to think on your own. 0.0526. Doing something very interesting here. Here's what I want you to think about. When we're saying that P equals 1/3, okay, that's two-tailed test because it's equal to. When we're claiming a null hypothesis that the probability is equal to 0.33, then our alternative hypothesis is that it's not equal to 0.33. And when we have not equal to, it could be less than or it could be greater than. So suddenly I'm interested in this. I'm interested in the area to the left, but I'm also interested in the area to the right. So before I was only looking at one side because the claim was less than, but the claim is equal to, then we have to look at the two other ends, because if it's not equal to, it could be less than, it could be more than. So I have to find the area of this Jimmy Jam, and then I have to double it to get the area total. And I was doing that just now quickly, but I'm about to show you what it is. So I'm going to go to normal CDF, hit enter. I've got 0 and 1. My lower bound is negative infinity. My upper bound is negative 1.62, and then I hit calculate. And what I got for this area right here is 0.0526, which means this area is also the same because they're the same on both sides. So if I take that 0.0526 and times it by 2, or add those two things together, the total area that I get for both areas added, the sum of those two areas, is 0.1052. So that's my p-value. It's confusing because we have p, which is the proportion, we have p hat, which is the sample proportion, we have p-value, which is the area, so it's confusing, right? It is. But anyway, our p-value is 0.1052. And we're supposed to be comparing that to 0.05. That happens to be greater than 0.05. 10% is way greater. Since the p-value is high, what would we do with the null? It would fly. We would think it's probably true because this is very likely to happen by chance. Okay, that's what that says. If it's more than 5%, we could, if what you're saying is true, this could just happen by chance then. So there's my p-value, which was 0.1052. Now the second thing is, what are the critical values? The critical values in this case, there's 2. In the last case we had 1 because we were just looking at a one-tail test, just less than. But now we're actually interested in a two-tailed test. And so we're interested in the critical values are on either side. So these are usual values, and there's unusual over here, and there's unusual over here as well. So we want to find out what both of those values are, because those are the values that separate our usual and our unusual. So because we had 0.05, but 0.05 is in 2 tails, right? So when I go to enter that, I have to keep in mind whether I have a one-tailed test or a two-tailed test. And when I enter, oh, I didn't show you on there. Okay, so I'm talking about inverse normal because I know the area and I want to find the z-score. That's what inverse normal does for us. And instead of thinking of it as just the 0.05, I'm thinking about that divided by 2. And so I get 0.025. And of course, mu is 0 and sigma is 1. And when I put that in, put this in, 0.025 for the area, mu is 0, sigma is 1, and hit calculate, then I get negative 1.96. I mean, if I round that, I'm going to round that to negative 1.960 if they want to go out 3 places. So here's this, negative 1.960. Why did I just get 1 and why did I get the negative 1? Well, remember, when you're doing inverse normal, it always assumes that you're talking about the area to the left or over here on the end. So it assumed you were talking about that one. But because we're splitting those up tails into 2 even parts, that's just going to be the same over here, only positive. So our 2 critical values are the negative 1.960 and positive 1.960. And that tells us that it makes sense that our value was usual, and we wouldn't get rid of the null hypothesis. It's something that happens because our value was over here. 1.62 was to the right of our cutoff. This critical value is that separating point, right? And that's it was to the right of that, and so to the right, and look, you're looking at me that way, and that means it's in the usual range. And if it's usual, then we say, oh, that's typical, it could happen, and we believe the null hypothesis, so we would let it fly, right? So there's that. This is not easy, and I'm like, oh, it's just that, blah, 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 and also, I'm talking to you, and I make mistakes, and I correct myself, and I know that. not cool. But at the same time, don't give up, you know, just be calm and things will happen. I'm looking for the number 10. Oh, here it is. So, page 16, number 10. And it's sort of good not to have everything handed to you without a little bit of a struggle. You know, a struggle is what makes you remember things. Making mistakes helps you remember. There's 45 pages for these 25 questions. So bad for the environment. But anyways, this is how we're doing it. Assume that a significance level is 0.1. Okay, that's different now. We've been using 0.05. This is 0.1. They can tell you whatever significance level they want. That's all you're doing is comparing your p-value to that, so no big deal. Use the given information to find the p-value and the critical values. So they're saying that p does not equal 2/5. That's what their claim was. Okay, so that's the alternative hypothesis. So our actual hypothesis is that p does equal 2/5. That's what we're talking about. 2/5 is the same as 0.4, right? So they're saying that that's what it is. Okay, so we're going to look at our test statistic to find the p-value. The p-value is the area that we find associated with that particular z-score. So over here is negative 1.79. That's our z-score. We know that this would be 0 right here in the middle. And since they're saying does not equal as the alternative hypothesis, we're also interested, this is a bad drawing, but anyways, we're also interested in positive 1.79, right? Because if it doesn't equal, then it could be less than, could be greater than. So we're looking at both of those. We can find the area to the left, and that's going to be the same as the area to the right. My drawing doesn't terribly suggest that, but that's what it is. If I go to normal CDF, and I have the 0 and the 1, and then I have a lowercase of negative infinity, and my upper bound is negative 1.79, then I can hit calculate, and I get the 0.0367. I would get the same thing if I did it over here. I'll do it just so you can see, but I would get the same answer if I did it this way. Let's do this, go down to normal CDF, this and this, and now I'm saying, well, my lower bound is 1.79, and I'm going forever to infinity. So I have 1.79 for my lower, I have infinity, positive infinity for my right, and look what answer I get, the same, 0.0367. So that's why I don't do it a second time, because I know it's going to get the same answer. But then what I want to do is take this 0.0367 and times it by 2. And that gives me a total, the sum of those two, which is what my p-value is the sum of those two things, 0.0734. That's my p-value. Okay, and that's the first thing that they ask for, 0.0734. When they talk about the area under the curve, probability under the curve, the p-value, those are all the same things, and they usually like them to 4 decimal places. The critical values, well, first of all, what would we do with that p-value? Would we make the null fly, or would we make it go? Well, 0.0734 is greater than, no, we don't have 0.05, it's less than, sorry, it's less than the 0.1 that we were given. Since this is low, the null will go. That means we don't believe the null hypothesis, because our information suggests that it's very unlikely to happen in comparison to our level of significance anyway. What about those critical values? The critical values are the points that separate the usual from the unusual. And we're talking about 0.4, talking about 0.1, but we have 2, it's in 2 areas, so it's 0.05 on each end, right? So we have 0.05 down here, and we have 0.05 up here. Now these are usual, and these over here are the unusual. All All right, so we want to find out what is that value that separates the usual from the unusual. And we do that by looking at our significance level. What I saw was that it was 0.1, so I divided by 2 to get the 0.05 because it was a two-tailed test, one on each end. So I have the area, second function data, and I'm going to do inverse normal. My area is 0.05. Hit calculate, and I get negative 1.645 and positive 1.645. Now on this one, they said go to 3 places, and they got 1.645. Okay, so those are our two z-scores, and when you put them in the computer, you're going to do negative 1.645, positive 1. Your answers, of course, could be different because they could give you a different significance level, but that's how you would answer them. You don't need to put parentheses around them, sorry. You just put them in without the parentheses, actually. But put a comma, but no space. All right, that's it. We did several of those in a row because they're confusing, because, you know, they just are. So you have a chance to see those again then. Okay, this is 10 finished. This is 10 continued. Where's 11? There we go. All right, number 11. Assume a significance level of 0.05. That's the most common one. Okay. Original claim, the proportion of male golfers is more than 0.6. The proportion, that's the claim. The proportion of male golfers is more than 0.6. What would our null hypothesis look like here? Well, it's a proportion, so it'd be P. And we always use the equal for that. So we'd be looking at 0.6. And we're saying, well, they're claiming that it's more than, so we can check to see if it's actually less than 0.6. All right, so the test results in a p-value of 0.132. P-value is 0.132. 0.132 is greater than our level of significance, which is 0.05. That means it's high. I'm getting less and less, writing less and less down. Whoa, that was, I don't know. That means that we're going to let that thing fly. The null hypothesis will fly. I don't know what I was drawing there. Okay, so if we let it fly, then we don't reject it. We fail to reject it. That's the word for it, okay? So we reject or we fail to reject. So we don't reject because it was high. We fail to reject it. We think it's probably right. Because the p-value is less than, no. We failed to reject it because the p-value is greater than. That was number C. Without using technical terms, state a final conclusion that addresses the original claim. Which of the following is the correct conclusion? Okay, if we let the null hypothesis fly, in other words, we don't reject it, that means that we think that the null hypothesis is probably true, and therefore we don't believe their claim. There is sufficient evidence to reject the claim that the proportion of male golfers is more than 0.6. There is sufficient evidence to support the claim. There is not sufficient evidence. Okay, we're not supporting the claim. We're supporting this one. We're saying let that one fly. We're failing to reject that one, which means, boo, we don't like the claim, right? That's what that means. If we support the null hypothesis, that was supposed to be a star, and I really can't draw one, obviously. If we support the null hypothesis or we don't reject it, then we don't support the other one. We can't have both. So we don't think it's this one. There is sufficient, no. So it's got to be one of these. It's not sufficient. Not sufficient evidence to support it that the g is more than 0.6. There is not sufficient evidence to reject the claim that the proportion of it is more than, there is not sufficient evidence to, yeah, we never reject the null, we never reject the alternative. Once they throw that in there, forget that. So it's got to be B, this one. I'm going to go back here and change that, sorry. So anyway, C and B. They didn't ask us to do that, and they write them a little more, they write them pretty clear when they're asking you, but anyway, I just wrote that down. But anyway, we are supporting this one, which means there's not an evidence to support this one. For the null hypothesis, we use the words reject, or we use the word fail to reject. For the alternative hypothesis, we use support or evidence to not support. No evidence to support. You see how those words support go with the alternative, reject go with the null hypothesis. So that's an important distinction to make. Okay, let's go on to number 12. Trying to get rid of the extra pages in the middle. We got page there, page there. This is a whole other page. And then we go over here to this page. Okay. We're halfway finished, so I think maybe I should stop after half because it's a long video and whatever. But we're getting to the good part. We're getting to the part where we actually get to make some decisions about people's claims, which is nice. Okay. A 0.01 significance level is used for a hypothesis test of the claim that when parents use a particular method of gender selection, the proportion of baby girls is greater than 0.5. Assume the sample data consists of 45 girls and 81 births. So the sample statistic of 5 nines results in a z-score that is 1 standard deviation above 0. Complete parts A through and blah, blah, blah. Okay. First of all, what's the value of alpha in here? No, that's the second question. Sorry. What's the value, what's the null and alternative hypothesis? Remember that the null hypothesis uses the equals, and the alternative hypothesis uses the inequalities or the does not equal symbol. So what I'm saying that is looking at D, no way, because D has a does not equal sign for the null hypothesis. For the null hypothesis, the only thing that we're going to use is equal, less than or equal to, a greater than or equal, and we're actually just focusing on this one. So I'll make it easier for you. Your answers are going to have equal for the null hypothesis. And then the other, they were saying their claim was they're claiming greater than, which means they claim the alternative hypothesis, which is this one. So they have, the null hypothesis is that normally we expect it to be 0.5, and they're saying ours is greater than 0.5. Alpha here is the significance level, and that's given in the problem. So that's just 0.01. That's just all they're asking for there. What is the sampling distribution of the sample statistic? Would we use a normal distribution, which is the Z, student T distribution, or the chi-squared? Those are our three choices. Well, do you see how they're using P, right? And so we have, obviously we know in the population what the standard deviation and mean is of births, because it's been done since John Bronte did it back in England, back in whatever. So we know that. So we do know something about the population here. So it's a normal distribution. Is the test two-tailed, left-tailed, or right-tailed? All you have to do to answer that is look at your alternative hypothesis and look at the symbol that we're using. If it's a greater than symbol, then it's right tail. If it's less than, then it's left tail. And if it's this, then it's a two-tail. That's always what we're looking at with the alternative hypothesis to answer that kind of question. Since they're claiming greater than, then it's a right-tailed test. What is the value of the test statistic? Well, they gave us that because they told us we have a z-score. This is so annoying. they told us that we have a z-score that is 1 standard deviation above, which means that our test statistic, our z, is 1. That test statistic is just the z-score associated with those particular values. What is the p-value? Well, the p-value and bad drawing. Here's our p-value, or z-score of 1. We're talking about a right-tailed test. We're talking about stuff to the right. So we're interested in the area to the right of 1. We have to know it's a left or right-tailed test in order to get that. And that is, we're given this, we want to find the area. That's a normal CDF problem. So we say second function data, distribution, normal CDF. We have 0 and 1. And then our lowest range value is 1, and our greatest is infinity. And then we hit enter twice. And that gives us this area, which is 0.1587. And that's our p-value. A p-value is just the area that we're particularly looking at. What's the percentage of the time that it's going to fall into that area, right? So 0.1587 is our p-value. What is the critical values? Well, I've showed you how to do that several times. The critical value is what we're going to find when we take 0.01 over here. I didn't divide that by 2 because it's just a right-tailed test. It's going to be one critical value and it's going to be positive. So be careful about that, because when you put it into the calculator, it's going to give you the negative value. Why? Well, we have inverse normal situation here because we're given the area and we're trying to find that z-score, or that cutoff score between the usual and the unusual, right? And so when I do this, I get 0.01. The calculator thinks you're talking about this piece over here. That's what it's going to assume. That's what the table assumes. And so when we get the negative, we have to say, but actually we know for sure that our value is over here on the right, so it's going to be positive. So I know my calculator can't read my mind. And my calculator gives me this, it gives me negative 2.326. And so when I round that to 2 places, I'm going to go over here and go, but wait, I am way to the right of 0. So I definitely am positive 2.33 rounded to 2 places. So my critical value is 2.33, right? So I've been doing it. The critical value, what is the area of the critical region? Well, how do you find the area of the critical region? Well, we just found it. It's given. The area is this. We already were told the area of the critical region, and then we know what the value is associated with that area. So no worries. We don't have to do any work for that. You could put it back in and see, but the area is that, because we know by looking at this picture, the area is 0.01 associated with that to the right of that. All right. So kind of interesting. Getting to some interesting stuff, but also I'm not delusional about it. It's challenging too. So let's see. 13 is hidden away. Here we go. There's 13. Let's see what 13 is about. That would put us halfway through anyway, which I wanted to get at least halfway through. 12 and a half would get us through. We'll do half of this one. No, not really. I want to talk about a type 2 error and a type 1 error again, because you might have seen it in the notes, but a type 1 error is when you reject the null, when the null is true. Okay, that means that you made an error, obviously. You rejected something when you shouldn't have. It was actually true, but we rejected it and said it wasn't. That's a type 1 error, right? Type 1 error is rejecting the null when it's actually true. A type 2 error is when you fail to reject. Remember, those are the only 2 things we can say for that. We fail to reject when the null is false. FF, fail, false. That's how I can help remember that. That's type 2, fail, false. There's 2 F's in a type 2, fail, and it's false. So that might be helpful to you, maybe not, but that's how I remember it. 2 F's, in the type 2. Fail to reject when it's actually false. Anyway, maybe you can just write it down on paper and then you don't have to have those little things, whatever. Which of the following is a type 1 error? You reject, okay, see where it says fail to reject? Forget that. That can't be a type 1 error. Type 2 errors are the ones that start with fail to reject. So that one, I know that. Okay, so we know for sure we can get rid of those as we talk about type 1 and type 2. We reject the claim that the proportion of settled malpractice suits is 0.33 when the proportion is actually. So we rejected it, but it was actually true. That sounds like it to me. What's this one say? Reject it when the proportion is different. No, we should have rejected if it's different. That would have been good. That wouldn't have been an error. That would have been like good for you. So then we come down here. A type 2 error is when we fail when it's false. We fail to reject when the proportion of settled amount is 0.3 when the proportion is actually different. That sounds like it, right? Because I failed to reject it even though it's actually different. It wasn't true, but I failed to reject it. That's bad. So AA, yeah. Type 1, type 2. We always talk about those, but I'm going to just do a couple of more. In a Harris poll, adults were asked if they are in favor of abolishing the penny. Among the responses, 1,266 answered no, 462 answered yes, and 393 had no opinion. What is the sample proportion of yes responses, and what notation is used to represent it? Well, the sample proportion is used p hat. So we could forget about this and forget about that. It's got to be p hat. How would you find p hat here? Well, you would take the 1266 that you had, and you're looking at, oh, we don't know 1266. That's 1266 was just the no, so we have to do this. Plus the 462 plus the 393. That's the total responses. The ones that answered yes were just these, 462. So 462 divided by that sum gives you the proportion, and it turns out to be C, which is 0.218. I'm not calculating that for you, but I'm sure you can do it on your own. Okay, we will stop because 15 starts into some more, a little more intense stuff. And I'm not saying the rest of this wasn't hard, but you know, it could get a little harder. So have a great day. I'll see you next time for the second half.